Welcome to week 5. Last week we have discussed the dominant PV technology in the current market, the PV technology based on crystalline silicon wafers. I'm confident that this technology will stay the dominant PV technology in the market for a long time to go. This week we will look into the alternative PV technologies like the thin film technologies, also referred to as the second generation PV technology. Discussing these PV technologies in detail can easily fill an entire course. Due to time limitations, I will provide you with a general introduction into the various PV technologies. I will focus on the working principles of the various devices, the current status, and the future challenges of the various technologies. I would like to start with the 3-5 PV technology. This is the solar cell technology which results in the highest conversion efficiencies under both one-sun standard test conditions and concentrated sun conditions. It is mainly used in space technology and in concentrated technology. As some concepts use crystalline germanium and gallium arsenide wafer as substrate, it might not be a real thin film PV technology, like thin film silicon, cadmium telluride, CIGS or organics, which will be discussed later this course. However, the 3-5 based absorber layers itself can be considered as thin in reference to the crystalline silicon wafers. The 3-5 materials are based on 3 valence electron elements like aluminum, gallium and indium, and the 5 valence electron materials as phosphorus and arsenic. Various different semiconductor materials such as gallium arsenide, gallium phosphide, indium phosphide, indium arsenide, and more complex alloys like gallium indium arsenide, gallium indium phosphide, aluminum gallium indium arsenide, and aluminum gallium indium phosphide have been explored. Let's consider for the moment the standard gallium arsenide semiconductor material. Its lattice has a tetrahedral diamond lattice structure just like silicon. However, every gallium atom neighbors 4 arsenic atoms, and every arsenic atom neighbors 4 gallium atoms. Compared to silicon, it has a slightly larger lattice constant and is significantly heavier than silicon. Both gallium and arsenic are roughly twice as heavy as silicon. Here we see the electronic band dispersion diagram again. We can easily see that the band gap of gallium arsenide is a direct band gap material. The highest energy level in the valence band is vertically aligned with the lowest energy in the conduction band. It means that only transfer of energy is required to excite an electron from the valence to the conduction band. No transfer of momentum is required. The direct band gap transition is around 1.42 electron volt, which is the band gap of gallium arsenide. Here we look again at the absorption coefficient versus the wavelength. As you can see here, the absorption coefficient of gallium arsenide is significantly larger than for silicon. As example, we also show the 3-5 material indium phosphide. It means that to absorb the same amount of light in reference to a silicon wafer, the thickness of the gallium arsenide film can be more than an order of magnitude thinner. Another advantage of the direct 3-5 semiconductor materials shown here is that the band gap is relatively sharp. The absorption coefficient increases quickly above the band gap energy. If we look at the utilization of the band gap energy, due to the direct band gap properties, radiative recombination processes can become an important recombination mechanism as well. The Shockley-Reed-Hall recombination can be kept low as the typical epitaxy processes used to deposit 3-5 films results in high purity films. Why does the 3-5 technology result in high conversion efficiencies? The 3-5 technology PV devices are based on the multi-junction concept. more than one bandgap material is used. As discussed in week 4, using only one single bandgap material, the theoretical efficiency is limited by the Shockley-Queisser limit. Either a large fraction of the energy of the energetic photons are lost as heat, or the photons below the bandgap are lost as they are not absorbed. In this illustration, you see a low bandgap material. A large fraction of the energy carried by the photons is not used. However, if you use more bandgaps, you see that the same amount of photons can be used and less energy is wasted as heat. Consequently, simultaneously large parts of the solar spectrum and large parts of the energy in the solar spectrum can be utilized by using more than one p-n junction. Here you see an illustration of one of the typical 3-5 triple junctions. It is based on a low bandgap material, a germanium substrate wafer. Note that germanium has a bandgap of 0.67 electron volts. The middle cell is based on gallium arsenide and has a bandgap of 1.4 electron volt. The cell at the top is based on gallium indium phosphide with a bandgap in the order of 1.86 electron volt. How does a multi-junction solar cell work? The p-n junction at the window layer at which the solar light enters the PV device is called the top cell. As the spectral part with the most energetic photons like blue light has the smallest penetration depth in materials, the high bandgap junction always acts like the top cell. As the near-infrared light outside the visible spectrum has the largest penetration depth, the bottom cell is the cell with the lowest bandgap. This cell has to harvest the photons from spectral part with the lower energetic photons. Here we see the JV curve of 3 single p-n junctions. p-n junction 1 has the highest open circuit voltage and the lowest short circuit current density. This means this p-n junction has the highest bandgap. p-n junction 3 has a low open circuit voltage and a high current density. Consequently, it has the lowest bandgap. p-n junction 2 has a bandgap in between. If you would like to make a triple junction out of these 3 p-n junctions, p-n junction 1 will act as the top cell, p-n junction 2 will act as the middle cell, and p-n junction 3 will act as the bottom cell. What would the JV curve of a triple junction look like? First, we will consider the equivalent electric circuit. Here we show the equivalent electric circuit of an ideal single junction solar cell. Every p-n junction in a multi-junction solar cell can be represented by this circuit. However, how will these solar cell circuits be connected in the representative multi-junction circuit? Will the cells be connected in series, or are the 3 cells connected in parallel? Take a few seconds to think and answer. In a parallel circuit, the voltage over all solar cells is equal and the currents do add up. However, the various solar cells have different bandgaps and therefore different open circuit voltages, going from high voltage for the top cell down to a low voltage for the bottom cell. Secondly, the current density generated in all cells have to conduct through all 3 cells to be collected at the front and back contacts. As a result, the multi-junction can be interpreted as a series connection of single junction solar cells. Now we return to the question, how does the JV curve of the triple junction look like? The voltages of the individual cells add up in the triple junction like in a series connection. The current density in a series connection is equal over the entire solar cell. This means that the current density is determined by the p-n junction generating the lowest current. The resulting JV curves look like this. The voltages add up and the current is determined by the cell delivering the lowest current. Let's look at a typical band diagram of such triple junction. Here you see the top cell with high bandgap at the left hand side and the bottom cell at the right hand side. However, the band diagram would not look like this in reality. If we place 3 p-n junctions in series, it means that the p layer of, for instance, the top cell and the n layer of the middle cell form a p-n junction as well. This p-n junction is in the reverse direction compared to the p-n junctions forming the 3 single junction solar cells. This would significantly lower the voltage of the total triple junction. The creation of such reverse junction can be prevented by the inclusion of a so-called tunnel junction. It provides a low electrical resistance and has a high bandgap to prevent any parasitic absorption losses. The high bandgap tunnel junction is relatively thin. It means that the valence band at one side is lined up with the conduction band at the other side of the tunnel junction. The depletion zone of such junction is extremely narrow. As a result, the slope of the valence band and conduction band are so steep that the electrons from n layer tunnel through the small barrier to the p layer, where they recombine with the holes. Important is that the resistance of the tunnel junction is low, resulting in a low voltage loss over the tunnel junction. Looking at a triple junction, it means that the holes in the p layer of the top cell have to recombine with the electrons of the n layer of the middle cell. The holes in the p layer of the middle cell have to recombine with the electrons of the n layer of the bottom cell. The electrons of the top cell are collected at the front contact and the holes in the p layer at the back contact. This demonstrates that the recombination current at the tunnel junctions represent the current density of the triple junction. The cell producing the lowest current will determine the current density of the cell, just like we expected for series connected cells. Let's move to the processing of 3,5 semiconductor materials. High quality 3,5 semiconductor materials can be deposited using epitaxy deposition methods. Epitaxy is a deposition method in which a crystalline overlayer is deposited on a crystalline substrate, where the overlayer adopts the crystal lattice of its substrate. The precursor atoms are provided by various element sources. For instance, like in this illustration, gallium arsenide is epitaxial deposited. Gallium and arsenic atoms are directed to a growth surface under ultra-high vacuum conditions. The substrate is usually a germanium substrate. The gallium arsenide crystalline lattice is grown layer by layer and adopts the structure of the crystalline substrate. The relatively slow layer by layer growth allows the deposition of compact materials without any vacancy defects. Furthermore, processing at high vacuum conditions prevents the incorporation of impurities. Dopants can be added to make it N-type or P-type. 3,5 semiconductors can be deposited up to a very high degree of purity. In general, metal organic chemical vapor deposition, abbreviated as MOCVD, is used to deposit the 3,5 semiconductor layers. Typical precursor gases are 3-methyl gallium, 3-methyl indium, 3-methyl aluminum, arsine gas and phosphine gas. Surface reactions of the metal organic compounds and hydrides containing the required metal chemical elements creates the condition for the epitaxial crystalline growth. The deposition method is expensive, as similar techniques are used to make 3,5 based semiconductor devices on the scale of chips. A challenge of making these crystalline 3,5 semiconductor materials is that their lattice constants of the various materials are not the same. As you can see in this graph, with on the vertical axis the band gap and on the horizontal axis the lattice constant, every semiconductor material is unique. There are no two different semiconductor materials that have the same band gap and the same lattice constant. This means that interfaces between these materials show a mismatch. Not every valence electron is able to make a bond with a neighbor. However, the triple junction I have introduced earlier based on gallium indium phosphide, gallium arsenide and germanium is a lattice-matched solar cell. What do I mean with that? Let's look again to the phase diagram of semiconductors where the band gap is plotted versus the lattice constant. The triple junction is processed on a p-type germanium substrate. The bottom cell is a germanium cell. On top of this, you would like to place a junction that has first the same lattice constant and secondly a higher band gap. As you can see, gallium arsenide has exactly the same lattice constant as germanium. This means gallium arsenide and germanium can make good interfaces without any coordination defects related to mismatched lattices. To have a reasonable current matching, the desired band gap of the top cell should be around 1.8 electron volts. However, we see that no alloys based on Soli2 elements exist with a band gap of 1.8 electron volt. However, if we take a mixture of gallium, indium and phosphorus, we see that we can make a 3,5 alloy with a band gap of 1.8 electron volt and which has a matching lattice constant with gallium arsenide and germanium. Consequently, triple junctions based on gallium indium phosphide, gallium arsenide and germanium can be fully lattice matched. Here you see some specs of a typical lattice matched triple junction under AM0 sunlight exposure with an irradiance of 135 milliwatts per square centimeters of SpectroLab. The total open circuit voltage is 2.6 volts and the short circuit current density is 17.8 milliamps per square centimeters. This means that up to a band gap of 0.67 electron volts, we have a spectral utilization expressed in current densities of 53.4 milliamps per square centimeters. Theoretically, this spectral part can generate 62 milliamps per square centimeters of current with an EQE of 100%. This means that this triple junction of SpectroLab has an impressive average EQE of 86%. Having a fill factor of 85%, this cell has a 29.5% conversion efficiency for AM0 space conditions. The EQE of a triple junction would look like this. Note that this graph is a simulation of a gallium indium phosphide gallium arsenide germanium triple junction solar cell. The spectral utilization of the various subcells approaches the shape of block functions. You have to realize that the fact that 3,5 materials have sharp band gaps and have high absorption coefficients is really helpful in designing these triple junctions. As you can see, the bottom cell generates much more current than the middle and the top cell. This ineffective use of the near-infrared part can be improved when we move to quadruple junctions. Here you see the example of the EQE of a quadruple junction measured at the Fraunhofer Institute. As you can see, an additional cell is placed between the middle and bottom cell of the triple junction. Currently, the energy utilization out of the spectrum is further improved by moving to multi-junctions of 5 to 6 solar cells. A challenge with going to so many junctions is that the lattice matching can not be guaranteed anymore. These types of lattice mismatch multi-junctions are called metamorphic multi-junctions. It requires buffer layers that have a profiling in the lattice constant, going from the lattice constant of one p-n junctions to the lattice constant of the next p-n junction. On the left, you see a lattice matched triple junction, and on the right, you see a metamorphic triple junction. Boeing's SpectroLab has demonstrated an impressive 37.8 conversion efficiency of a 5-junction solar cell under one-sun solar conditions. As the 3,5 PV technologies are expensive, they are used for space applications and in concentrator technology. The dollar per watt peak of a small expensive 3,5 multi-junction device can be improved by concentrating the irradiance of a large area on the small solar cell device. Advantage of concentrating sunlight is that the open circuit voltage is increased with irradiance as well, as long as Auger recombination of light-excited charge carriers does not become dominant. Important is that the small solar cell devices have to be actively cooled. As will be discussed in week 7 and 8, the performance of PV devices goes down when they heat up. This loss in performance is a result of the increasing dark current of the diode component of a PN junction. Furthermore, concentrator solar cells need sun tracking systems. These systems make sure that the optical concentrator system tracks the sun and guarantees the optimal light concentration on the small PV device during the entire day. The non-modular cost of concentrator systems are consequently larger than that of conventional PV system based on crystalline silicon or on thin film technologies. The current record conversion efficiency on lab scale is 44.1% on the 942 concentrated sunlight conditions as achieved by solar junction. This was a quick overview of the 3.5 PV technology. In the next block, we will talk about thin film silicon PV technology. Last week we have discussed the dominant PV technology in the current market, the PV technology based on crystalline silicon wafers. Now we will discuss a different silicon technology, the thin film silicon PV technology, which belongs to the so-called second generation PV technology. As discussed in week 1, these PV technologies are focused on reducing the cost price of the PV module to a level where the cost price per watt peak drops below that of crystalline silicon technology. An advantage of thin film silicon solar cells is that they can be deposited on glass substrates and flexible substrates. So the first question we have to answer is, which type of silicon alloys are being used as an absorber layer? The typical lattice structure is either amorphous or nanocrystalline. Nanocrystalline is also called microcrystalline in the literature. In a moment I come back how these lattices really look like. A dashed is the abbreviation of amorphous, and C dash is the abbreviation for nanocrystalline silicon. First, I want to focus on the composition of the various alloys. We have hydrogenated amorphous silicon and nanocrystalline silicon. It means that we have a lattice of silicon in which some of the valence electrons are passivated by hydrogen. The column H in the abbreviation corresponds to the incorporated hydrogen. The hydrogen content for these types of silicon alloys typically ranges from 5 up to 15%. The second alloy is silicon mixed with the next element in the periodic table with 4 valence electrons, germanium. Both hydrogenated amorphous and nanocrystalline silicon germanium alloys are being used in thin film silicon solar cells. Silicon is also mixed using the 4 valence electron material carbon, leading to hydrogenated amorphous silicon carbide. Another interesting silicon-based alloy is that in which the 6 valence electron atom, oxygen, is incorporated in the lattice. This nanocrystalline silicon oxide is being used in thin film silicon solar cells as well. All these alloys can be doped. Even the nanocrystalline silicon oxide can be doped by p-type adding boron or n-type by adding phosphorus. How does an amorphous lattice look like? Last week we have discussed crystalline silicon. Crystalline silicon has an order lattice in which the orientation and structure is repeated in all directions. For amorphous silicon this is not the case. The lattice is disordered, as you can see in this animation. The animation shows the growth of a so-called continuous random network. On atomic length scales, or also called short-range order, the atoms still have a tetrahedrally coordinated structure. The silicon bond angles and silicon-silicon bond lengths are slightly distorted in reference to a crystalline silicon network. On short-range order, the lattice still might look very crystalline-like. However, at larger length scales, or also referred to as long range, the lattice does not look crystalline anymore. Here you only see a disordered network which is only built up out of silicon atoms. In real amorphous network you will have volume deficiencies in the lattice. Examples of volume deficiencies are vacancies, multi-vacancies or nanosite voids. The surfaces of these volume deficiencies are passivated with hydrogen. Another phase of hydrogenated silicon alloys is the nanocrystalline lattice. This is a heterogeneous material. It consists of small grains with a crystalline lattice. These grains are embedded into a tissue of hydrogenated amorphous silicon. Typical grain sizes are in the order of a few tenths of nanometers. This illustration, made by the Forschungszentrum in Jülich, Germany, nicely shows the various phases of thin film silicon going from the left to the right. At the right hand side, the phase represents the amorphous lattice. At the left hand side, a fully crystalline phase is shown, which is close to that of polycrystalline silicon, except that it has much more cracks and pores in it. Note that the nanocrystalline and microcrystalline silicon refers to the same phase. Going from right to left, the amorphous phase is changing into a mixed phase with a few small crystalline grains to a phase which is dominated by large crystalline grains and a small fraction of amorphous tissue. The best nanocrystalline silicon bulk materials used in solar cells has a network close to the so-called amorphous to nanocrystalline silicon transition, and its crystalline volume fraction is in the order of 60%. The bandgap of nanocrystalline silicon is close to that of crystalline silicon due to the crystalline network in the grains. The bandgap of amorphous silicon is larger in reference to crystalline silicon. It is out of the scope of this course to discuss this in great detail, but the distortions in bond angles and bond lengths make the bandgap larger in reference to crystalline silicon lattice. An important consequence of a disordered lattice is that the electron moment is poorly defined in contrast to crystalline silicon. In crystalline silicon, the electronic band diagram versus lattice momentum looks like this. Both energy and momentum transfer is needed to excite an electron from the valence band to the conduction band. Crystalline silicon is an indirect bandgap material. This bandgap does not hold anymore for an amorphous lattice. Therefore, the amorphous silicon does not act like an indirect bandgap material, but a direct bandgap material. This has a positive effect on the absorption of the hydrogenated amorphous silicon. It is more likely that a photon can be absorbed to excite an electron from valence to conduction band. This is demonstrated in the next graph. Here, the absorption coefficient is plotted versus the photon energy expressed in electron volts. The black line represents crystalline silicon. The green line represents amorphous silicon. The absorption coefficient for amorphous silicon is in the visible spectrum much larger in reference to crystalline silicon. It can be 2 orders of magnitude larger, which means that much thinner silicon films can be used in reference to the typical wafers in crystalline silicon solar cells. The red line represents amorphous silicon germanium, which has lower band gaps and much higher absorption coefficient in the visible. Hydrogenated amorphous silicon has a band gap in the order of 1.6 up to 1.9 electron volts, which can be tuned by the amount of hydrogen incorporated into the silicon network. Nanocrystalline silicon has a band gap in the range of 1.1 up to 1.3 electron volts. The band gap of the silicon alloy can be tuned by inclusion of the other elements as well. The hydrogenated amorphous silicon germanium alloys can have band gaps in the range of 1.4 up to 1.6 electron volts. Silicon mixed with carbon, the so-called amorphous silicon carbide, can have band gaps of 1.9 electron volts and larger. Nanocrystalline silicon oxides have band gaps larger than 2 electron volts. The hydrogenated amorphous and nanocrystalline silicon films have a relatively high defect density in reference to crystalline silicon. Due to the disordered structure, not all valence electrons are able to make bonds with the neighboring atoms. The so-called dangling bonds can act as defects. This means that the lifetime of the light-excited charge carriers is limited by the Shockley-Reed-Hall recombination, which controls the diffusion length. The recombination is so high that the diffusion length of the charge carriers in hydrogenated amorphous silicon is only 100 up to 300 nanometers. This means that the transport of charge carriers in a thick absorber layer cannot rely on diffusion. A typical amorphous silicon solar cell is therefore not based on a p-n junction like the wafer-based crystalline silicon solar cells. The amorphous silicon solar cell is based on a pin junction. What is a pin junction? The absorber layer is based on an intrinsic amorphous silicon absorber film which is sandwiched between thin layers of p-doped and n-doped amorphous silicon. The red layer indicates the p-doped amorphous silicon and the yellow indicates the amorphous n layer in this illustration of a single junction amorphous silicon solar cell. The p and n doped layers create a built-in electric field over the intrinsic absorber layer. This can be illustrated by an electronic Venn diagram of the amorphous silicon solar cell. The solar cell consists of a thin p layer with typical thickness of only 10 nanometers. Note that the Fermi level of a p layer is closer to the valence band than to the conduction band. The intrinsic film has a typical thickness of 100 up to 300 nanometers and its Fermi level is positioned in the middle of the band gap. The n-type layer is in the order of 20 nanometers and its Fermi level is closer to the conduction band than to the valence band. If these layers are connected together, we know that the Fermi level equals out in the dark and thermal equilibrium. This creates a slope over the electronic band in the intrinsic film, as you can see in this illustration. This reflects the built-in electric field. The light-excited charge carrier will move due to the electric field. The holes move up the slope in the valence band to the p layer and the electrons move down the slope in the conduction band to the n layer. Note that as the absorber layer is intrinsic, the charge carriers neither belong to the minority or majority charge carriers. The hole and electron density is in the same order of magnitude. In the p layer, the holes are the majority charge carriers and the dominant transport mechanism is diffusion. In the n layer, the electrons are the majority charge carriers and diffusion is the dominant transport mechanism. Due to the relative low diffusion length, both the p and n layers cannot be too thick. A wafer-based crystalline silicon solar cell, discussed last week, can be considered as a diffusion solar cell. Diffusion is the dominant transport mechanism for the charge carriers in the absorber layer. An amorphous silicon solar cell is a drift device. The dominant transport mechanism in the absorber layer is drift. Typical solar cells look like this. This is a solar cell in the superstrate configuration. If people talk about pin junctions, they refer to the sequence in which the silicon layers were deposited. So first the p layer, then the I layer, and then the n layer. The front contact is a transparent conductive oxide, abbreviated with TCO. Typical TCO layers are fluor-doped tin oxide, aluminum-doped zinc oxide, boron-doped zinc oxide, hydrogen-doped indium oxide, ITO, which is tin-doped indium oxide. These films are processed using either sputtering, low-pressure chemical vapor deposition, metal organic chemical vapor deposition, and atmospheric pressure chemical vapor deposition. P-doped layers are boron-doped amorphous silicon, but also the higher bandgap materials as boron-doped silicon carbide and silicon oxide layers are used to enhance the transmission of the bluish light into the absorber layer. As back reflector, usually a TCO metal back reflector is integrated into the device. Metals are either aluminum or the more expensive silver, which has a higher back reflection compared to aluminum. As the bandgap of hydrogenated amorphous silicon is relatively high in the order of 1.75 electron volt, it only has a spectral response below wavelengths of 700 nanometers. The best current density achieved in single junction amorphous silicon solar cells are 17 up to 18 milliamps per square centimeters, whereas the theoretical current available in the spectrum is in the order of 23 milliamps per square centimeter, which means that the spectrally average EQE is in the order of 74 to up to 77%. The best open circuit voltages are in the order of 1 electron volt. With respect to a band gap of 1.75 electron volt, the band gap utilization is relatively low due to the high levels of Shockley-Reed-Hall recombination and the relatively broad valence and conduction band tails. The best stabilized efficiency of a single junction solar cell is 10.1%, obtained by the research lab of Oerlikon Solar, currently part of Tokyo Electron. Nanocrystalline silicon films are used as intrinsic absorber layer as well in a PIN solar cell. The spectral utilization of the nanocrystalline silicon PIN junction is better in reference to amorphous silicon due to the lower band gap of the nanocrystalline silicon. However, to utilize the spectral part from 700 up to 950 nanometers, thicker films are required. Typical intrinsic film thicknesses are 1 up to 3 microns from nanocrystalline silicon. The maximum short circuit current densities obtained are 30 to 31 milliamps per square centimeters, as demonstrated by United Solar in the United States. The highest open circuit voltages are in the order of 600 millivolts. The record conversion efficiency for a single junction nanocrystalline silicon solar cell is 10.7%, as achieved by the EPFL in Neuchâtel, Switzerland. Both the single junction amorphous and nanocrystalline silicon solar cell do not have an optimum spectral utilization. For that reason, multi-junction concepts are being used in the thin film silicon field as well. One of the most studied concepts is the so-called micromorph concept, which is a double junction that consists of one amorphous silicon PIN junction and a nanocrystalline silicon PIN junction. How does such double junction solar cell work? First, the amorphous junction has the highest band gap of both materials and will act as top cell. The top cell is the PIN junction that is facing to the front and where the incident light is passing first. The cell with the highest band gap acts like the top cell, as the spectral part with the most energetic photons has the smallest penetration depth in materials. The bottom cell is the cell with the lowest band gap. This cell has to harvest the photons from spectral parts with the lower energetic photons. Let's look at a typical band diagram of such double junction, or also referred to as a tandem cell. On the left, the electronic band diagram of the amorphous silicon top cell is shown, and on the right, the electronic band diagram of nanocrystalline silicon bottom cell is shown. The bluish and green light is absorbed in the top cell and excite the mobile electrons and holes. The reddish light is absorbed in the bottom cell, exciting the charge carriers. Let's consider the two electron-hole pairs excited in the top and bottom cell. The hole generated in the amorphous top cell moves to the p layer. The electron excited in the bottom cell drifts to the n layer. Both can be collected at the front and back contacts. The electron excited in the top cell drifts to the n layer, and the holes generated in the nanocrystalline bottom cell drifts to the p layer. Similar like in the 3,5 multi-junction, the electrons and holes have to recombine at the recombination tunnel junction between the n layer of the top cell and the p layer of the bottom cell. Often, a very thin and defect-rich layer acts like a tunnel recombination junction here. Here, these electrons and holes recombine. Again, the total current density is equal to that of the junction with the lowest current density. It means that in an optimized multi-junction cell, all current densities in the various subcells have to be matched to achieve the best spectral utilization. Let's look to the JV curves of a single junction amorphous silicon solar cell and that of a single junction nanocrystalline silicon solar cell. The high band gap amorphous silicon has a high open circuit voltage of, let's say, 0.9 volts and a relatively low short circuit current density of 50 milliamps per square centimeters. Whereas the low band gap material of nanocrystalline silicon has a lower open circuit voltage of 0.5 volts and a higher short circuit current density of 25 milliamps per square centimeters. How would the JV curve of the corresponding tandem cell look like? If you would make a multi-junction of both components, we would get a cell with an open circuit voltage equal to the sum of the open circuit voltages of the individual single cells. The resulting current density of the double junction is lower than the currents in both bottom cells. The total current utilization of the tandem cell is determined by the bottom cell, which is 25 milliamps per square centimeters. Given the examples of the single junction here, the best current matching of both cells would deliver 12.5 milliamps per square centimeters. Here you see an example of thin film silicon based triple junction with an amorphous silicon top cell, an amorphous silicon germanium middle cell and a nanocrystalline silicon bottom cell as developed at United Solar. The colored part in the spectral power density function represents the utilization of the solar spectrum by the individual cells. Blue represents the top cell, green represents the middle cell, and red represents the bottom cell. In this figure you see the EQE of the 3 pin junctions of a record triple junction of United Solar. As you can see, the individual cells have various overlaps. They don't look like the block functions as we have seen for the 3-5 technologies. The light with the wavelengths below 450 nanometers are utilized by the top cell only. Wavelengths at 550 nanometers are utilized by the top cell and middle cell. Wavelengths at 650 nanometers are utilized by all 3 junctions. Wavelengths above 900 nanometers are only utilized by the bottom cell. Consequently, optimizing thin film silicon multi-junction solar cells is a complex interplay between the various thicknesses and light trapping concept used in the solar cell. In this slide you see the most studied and developed thin film silicon concept on lab scale. The record single junction amorphous silicon solar cell developed by Oerlikon Solar has an efficiency of 10.1%. The best single junction nanocrystalline silicon solar cell is 10.7% as obtained by EPFL in Neuchâtel in Switzerland. The best result for a micromorph double junction or an amorphous nanocrystalline double junction is 12.3% obtained by Oerlikon Solar. LG in Korea has the record for the amorphous nanocrystalline triple junction with 13.4%. United Solar achieved an initial efficiency of 16.3% for the triple junction based on amorphous silicon germanium and nanocrystalline silicon. However, the stability of the amorphous alloy used in this triple junction is a big issue. The hydrogenated amorphous silicon alloys suffer from light-induced degradation and the stable efficiency drops below that of 13.4% as achieved by the amorphous nano triple junction. The light-induced degradation, also referred to as the stable Wronski effect, is one of the biggest challenges for the thin film solar cells. The recombination of light-excited charge carriers generate some metastable defects in the absorber layers. More bulk defects means enhanced charge carrier recombination in the bulk, which mainly affects the performance of the amorphous solar cells. The performance of amorphous solar cells relatively decrease with 10 to 15% due to light-induced degradation. And therefore people talk about stabilized efficiency. If the stable Wronski effect could be tackled, thin film silicon devices could achieve efficiencies well above 16%. Another aspect of thin film silicon solar cell is the current matching between the various solar cells. Textured surfaces are being used to scatter light into the various junctions to enhance the absorption path length, which allows to use thinner absorber layers. This becomes more important for the bottom cell as this nanocrystalline silicon film is the thickest layer in the device and it has to absorb the most reddish part of the spectrum. Secondly, intermediate reflector layers are being used as a tool to manage the light management between the cells, like indicated by the blue layers. The top junction and bottom junctions are separated with a low reflective index material. Due to the large refractive index mismatch between this intermediate reflective layer and the top cell, more light is reflected back into the top cell. This allows the amorphous top cell to be made thinner and makes the device less sensitive to light-induced degradation. Nowadays, doped nanocrystalline silicon oxide layers are used as intermediate reflective layers. They have the bifunctionality of generating the built-in field over the absorber layers and to act as transparent intermediate reflective layers.
Let's go to the Demis lab at the Delft University of Technology. We will show how thin film silicon solar cells are made on lab scale. Before deposition, the samples have to be cleaned in a so-called ultrasonic cleaning bath. The potential dirt and dust particles are removed. Since the solar cell device is only several hundreds of nanometers up to a few microns thick, a dust particle on the substrate will generate a shunt between the front and back contact in the final solar cell. Here we use a substrate that is coming from the Japanese Asahi Glass company and already has a TCO coating on it. The TCO coating is a fluorine doped tin oxide and is responsible for the hazy color. In this movie, we deposit a thin zinc oxide layer on top of the Asahi substrate to protect the tin oxide from the next processing steps. The substrate is mounted on a sample holder and put into a load lock. A load lock is a chamber in which the substrate is brought under low pressure before it's moved into the processing chamber. This avoids the processing chamber to be contaminated with various unwelcome atoms and molecules present in ambient air. During sputtering, the zinc oxide target is bombarded using an ionized noble gas like argon. The generated aluminum zinc oxide species are sputtered into the chamber and deposited onto the substrate. Here you see the sputtering plasma. After the sputtering processing step, we have a glass plate with a tin oxide with on top a very thin zinc oxide layer. Next, the samples are mounted into a different substrate holder. This substrate holder is used during the plasma-enhanced chemical vapor deposition step to deposit the various thin silicon films. Again, we use a load lock. The load lock allows access to the various chambers. Every chamber is dedicated to deposit a type of silicon layer: P-type silicon carbide, intrinsic amorphous or nanocrystalline silicon, and N-doped amorphous silicon or N-doped nanocrystalline silicon. Typical precursor gases in the deposition plasmas are silane diluted with hydrogen. An RF bias between electrode plates generates a plasma. The silane is dissociated and the silicon containing radicals and ions are deposited on a substrate. Adding diborane or phosphine to the plasma makes the films P-type or N-type. Increasing the hydrogen content makes the films nanocrystalline instead of amorphous. The samples are moved from chamber to chamber through the load lock. After the various silicon deposition steps, the sample with a thin film silicon PIN junction on top looks like this. Next, the samples are covered by a mask. The mask determines the areas on the sample where the metal contacts are deposited. The samples are mounted into a processing chamber. Silver is used as source material and particles of silver are put in a boat. The silver is evaporated using an electron beam. The silver vapor deposits on the samples and form the back metal contacts. After taking the solar cell out of the E-beam evaporation setup, we can see the final silicon solar cell on lab scale. Every metal contact represents a solar cell.
The configuration of solar modules of thin film PV technologies are different from those based on crystalline silicon-based wafers. Here we will show the concept of how the solar cell in a thin film PV technology are processed and interconnected. We will show it here for a thin film silicon PV technology. In the next blocks, we will discuss other thin film technologies like CIGS and cadmium telluride. Similar interconnection schemes are being used for these technologies. The solar module and its interconnection is processed in one process sequence. The substrate carrier of the module is a large glass substrate. On the glass plates, the front TCO is deposited. Using intense lasers, lines of TCO are removed. This process is called laser scribing and determines the area of the solar cells. On top of the TCO, the various silicon layers are deposited, making the PV active part. After the silicon process step, a second laser scribing step is made. The metal back contact is deposited, after which the last laser scribe step is used. The whole cell is finished by covering it with an encapsulant material. In this interconnection scheme, the metal back contact is connected with the front zinc oxide contact of the next cell. A module consists out of long strips of solar cells which are interconnected. Here you see a picture of a micromorph tandem module. You can see the various solar cells and the laser scribes. The open circuit voltage of the module is determined by the number of solar cell strips that are connected in series. Note that shading effects on this type of module is different from that of wafer-based crystalline silicon solar cells. The best module efficiencies are in the order of 11% as achieved by companies like Tokyo Electron, Panasonic and Kaneka. Another advantage of thin film PV technology is that you have an option to deposit it on flexible substrates. Here I give an example of the Hyatt Solar company, who develops a technology that is deposited on a temporary aluminum foil. The entire solar cell is processed on the foil and encapsulated at the backside. Then the temporary substrate is etched away and the front side is encapsulated. This results in a very low weight flexible substrate which can be integrated in curved rooftop elements. The advantage of lightweight is that a professor can lift it quite easily. This technology can be installed on simple rooftop constructions that have a low maximum for the ballast weight. Compare this to glass-based solar panels. These can be quite heavy. Secondly, if the product is integrated into roof elements, it saves significantly on the installation cost, which has to become the largest contributor to the non-modular cost of a PV system. At the moment, only thin film silicon technologies have demonstrated flexible modules with reasonable efficiencies on lab scale. This was the quick introduction into thin film silicon PV technology. In view of time limitation, I did not talk about the thin film silicon junction crystalline solar cells. These are based on thermal crystallization of amorphous silicon deposited on non-wafer based substrates. On lab scale, close to 12% conversion efficiencies have been achieved with this approach as well. In the next block, I will talk about CIGS PV technology. This is the thin film PV technology which has the highest achieved efficiencies on both lab scale and module level. See you in the next block. The next thin film PV technology we will discuss today is based on CIGS. CIGS stands for copper, indium, gallium selenide sulfide. The typical CIGS alloys are heterogeneous materials. The physical properties of CIGS are rather complex, and many different views exist on these properties among scientists. Some important compounds in the material are copper indium selenide with a band gap of 1 electron volt, copper indium sulfide having a band gap of 1.5 electron volt, and copper gallium selenide having a band gap of 1.7 electron volt. These materials cover a wide range of both band gaps and lattice constants. The CIGS material is a direct band gap semiconductor material. Therefore, it has a large absorption coefficient. It requires only a thickness of 1 up to 2 microns to absorb a large fraction of the light above the band gap. Typical electron diffusion lengths are in the same order of a few microns. A variety of CIGS alloys exist, but the best performing layers have something in common. They contain a polycrystalline alpha phase. The lattice atoms are tetrahedrally bonded. Such a lattice structure is a so-called chalcopyrite structure, as you can see in this illustration. The heterogeneous material consists of a phase of copper-indium selenide, often indicated by CIS, and copper-indium gallium selenide. X is 0 means it is a copper-gallium selenide material, and X is 1 means it's a copper-indium selenide material. It means using the copper-gallium ratio X, the band gap can be tuned from the copper-gallium selenide at 1.7 electron volt at X is 0 down to 1 electron for X is 1. The CIGS absorber layer is a p-dope layer. The doping is a result of intrinsic defects in the material related to copper deficiencies. These vacancies officially act as an acceptor. It means electrons excited from the valence band can get easily trapped. As a result, the holes become the majority charge carrier density. Let's look at a typical CIGS solar cell structure. The substrate is glass. On top of the glass, a molybdenum layer with typical thickness of 1 micron is deposited, which acts as the back contact. On that, the p-type CIGS absorber layer is deposited, with thickness ranging from 2 up to 4 microns. The PN junction is formed by a thin N layer of around 50 nanometers on top of the p-type CIGS that is based on cadmium sulfide. This layer is referred to as the buffer layer. The N-type region is extended with an N-type TCO. First, an intrinsic zinc oxide is placed, followed by an aluminium-doped zinc oxide. The aluminum doping makes the zinc oxide N-type. Similar to some concepts of the thin film silicon technology, the aluminum-doped zinc oxide acts like a transparent front contact for the solar cell. On top of this transparent conductive oxide, anti-reflective coatings can be placed as discussed for the crystalline silicon technology. Here we see the electronic band diagram of a CIGS solar cell. The light enters the cell from the left at the zinc oxide side. The p-type CIGS absorber layers used in industrial modules have a typical band gap of 1.1 to 1.2 electron volts. This band gap is accomplished by a ratio of gallium to indium of around 0.3. The N-type cadmium sulfide buffer layer has a band gap of 2.5 electron volts. Since the band gap of the N and p-type junction materials are different, this CIGS cell can be considered as a heterojunction. The light-excited minority electrons in the CIGS layers have to diffuse to the cadmium sulfide CIGS interface to be separated. The holes diffuse to the molybdenum back contact to be collected. Here, the holes recombine with the electrons supplied from this molybdenum back contact. Zinc oxide acts like the front contact. The band gap of the zinc oxide is very large, minimizing the parasitic absorption losses in this device. The electrons have to be separated at the CIGS cadmium sulfide interface. As with every interface, this interface has more defects and could act as a loss mechanism to the minority electrons. This can be prevented by placing an N-type CIGS type of layer between the p-type CIGS and the cadmium sulfide interface, which screens the cadmium sulfide CIGS interface from the holes. The N-type CIGS is an indium-rich alloy like copper, indium gallium 3 selenide 5. In copper-deficient p-type CIGS materials, the dominant recombination mechanism is Shockley reed-hole recombination in the bulk. In contrast, in copper-rich CIGS films, the Shockley reed-hole recombination at the CIGS cadmium sulfide interface becomes dominant. One of the important aspects of CIGS solar cells is the role of sodium. Low contamination of sodium appears to increase the conductivity in the p-type CIGS materials. It leads to a welcome texture and an increase in the average grain size. Similar to multicrystalline silicon as discussed last week, the larger the grain size, the less grain boundaries and less recombination are present in the material. This results in higher bandgap utilization and higher open circuit voltages. Typical optimum concentration of sodium in the CIGS layers is 0.1%. The sodium source in the growth mechanism can be the soda lime glass used as substrate. In CIGS solar cell concepts, where this soda lime glass is missing, the sodium has to be intentionally added during the deposition process. In the CIGS field, the exact reason why sodium improves several properties of the CIGS is still under debate. In contrast to the thin film silicon technology discussed earlier, CIGS films can be deposited using a variety of deposition technologies. As many of these activities are developed within companies, not much detailed information is available on many of these processing techniques. One of the processing techniques is co-evaporation or co-sputtering under vacuum conditions. Using various targets of copper, gallium and indium, the precursors in various steps are co-evaporated onto a substrate. Two approaches can be used. First is the sputtering and co-evaporation on a substrate at high temperatures. During the process, there is an additional selenium source. During deposition, a CIGS film is formed. The second approach is sputtering and co-evaporation on a substrate at room temperature. The deposited films on the cold substrate are thermally annealed in presence of a selenide vapor to form the final CIGS structure. Another option is to deposit a selenium-rich layer on top of the initial deposited alloy, and this is annealed. Because of the variety and complexity of the reactions taking place during such selenization process, the properties of CIGS are difficult to control. Companies that use or have used the co-evaporation process are Worth Solar, Global Solar and Ascent Solar. Among CIGS companies using sputter approaches are Showa Shell, Solar Frontier, Avansis, Mia Soleil and Honda Soltec. An alternative approach is based on a kind of wafer bonding technique. Two different films are deposited on a substrate and superstrate. The films are pressed together under high pressure. When heated, the film is released from the superstrate and a CIGS film remains on a substrate. This processing technique is used by the company Heliovolt. Non-vacuum techniques are based on depositing nanoparticles of the precursor materials on a substrate, after which the film is sintered. Sintering is a process in which films are made out of powder. The powder is heated up to a temperature below the melting point. Atoms in the particles can diffuse across the boundaries of the particles. As a result, the particles fuse together, forming one big solid. An important advantage of the CIGS PV technology is that, on lab scale, it has achieved the highest conversion efficiencies among the thin film solar cells. Lab-scale CIGS solar cells processed on glass have a record efficiency of 19.9% as achieved by National Renewable Energy Lab in the US. Typical open circuit voltages are close to 700 millivolts, the fill factor of 81%, and short circuit current density between 35 and 36 milliamps per square centimeters have been achieved. The world record on flexible substrate has been obtained at the Swiss Federal Laboratories of Materials Science and technology. The CIGS cell on a flexible polymer foil resulted in an impressive conversion efficiency of 20.4%. A CIGS cell in a module are similarly interconnected as we have seen for thin film silicon cells discussed earlier. First, the molybdenum back contact is deposited on top of the glass substrate and the cell areas are defined by laser scribes. Then, the CIGS P layer and cadmium sulfide N layer are deposited, including a laser scribe step. Finally, the intrinsic and p-doped zinc oxide is deposited, followed by a final laser scribe step. Now, the front TCO electrode is connected with the molybdenum back contact of the next solar cell. The record efficiencies of modules are significantly lower than for the lab scale cells. Defining conversion efficiencies, we have to make a distinction between two types of numbers. The aperture area, which means that only the area of the PV active part is considered when the conversion efficiency is considered. Total area means that the entire module area is considered when calculating the conversion efficiency. This area includes the dead area created by interconnection and the edges of the module. The record efficiencies of 1 square meter modules are in the order of 13%, whereas the aperture area efficiency are just above 14% as confirmed by NREL. The German manufacturer Manz AG has presented a 15.9 aperture area efficiency and a total area efficiency of 14.6%. Solar Frontier in Japan claims a 17.8 aperture area efficiency on a very small module of 900 square centimeters. With these results, CIGS has the highest conversion efficiency achieved among the thin film PV technologies. However, as CIGS is a rather complex material with complex deposition processes over large areas, an important challenge for the CIGS PV industry is to achieve a high production yield of CIGS modules. Another challenge is that this technology includes the element indium. Here we see an illustration that shows the abundance of the various elements in the Earth's crust. The red line is an indication for the critical abundance of a source material to be used for a large-scale production. As you can see, indium is not a very abundant element as it lies below the red line. Therefore, indium might be the limiting step to upscale the CIGS PV technology to future terawatt scales. In addition, the current display industry depends on indium as well, as ITO is integrated in many display screens. Consequently, the interest in copper zinc tin sulfide, referred to as CZTS, is increasing to replace the CIGS absorber layer. CZTS is based on non-toxic and abundantly available elements. The current record efficiencies of CZTS solar cells or lab scale is around 11% as achieved by IBM. In the next block, we will discuss the thin film cadmium telluride PV technology. This is a PV technology which has currently the lowest demonstrated cost price per watt peak. See you in the next block. A third thin film technology we will discuss is the cadmium telluride. This thin film technology, which has currently demonstrated the lowest cost price per watt peak among all PV technologies. Let's start with the physical properties of cadmium telluride. This semiconductor material consists of the 2 valence electron element cadmium and the 6 valence element tellurium. Its network is a cubic tetrahedral lattice structure where every cadmium atom is bonded to a tellurium atom. A lot of the research activities on cadmium telluride have taken place on industrial level, and First Solar is the leading company in the cadmium telluride technology. The band gap of cadmium telluride is 1.44 electron volts, a value which lies within the optimal range of band gaps for a single junction solar cell. Cadmium telluride has a direct band gap. Consequently, only a few microns of cadmium telluride is required to absorb all the photons with an energy higher than the band gap. It means that the diffusion length for the charge carriers has to be in the same order to have the light excited charge carriers collected at the contact. N-doping of cadmium telluride can be achieved by replacing the 2-valence atom cadmium with a 3-valence electron like aluminum, gallium and indium. These elements act as shallow donors. N-doping is achieved as well by replacing the 6-valence tellurium atom with a 7-valence electron element like fluorine, chlorine, bromine and iodine atoms. They act as shallow acceptors. A tellurium vacancy acts like a donor as well. P-doping of cadmium telluride can be achieved by replacing the 2-valence atom cadmium with a 1-valence electron atom like copper, silver or gold. These elements act as a shallow acceptor. P-doping is achieved as well by replacing a 6-valence tellurium atom with a 5-valence electron element like nitrogen, phosphorus, arsenic. They act as shallow acceptors. A cadmium vacancy acts like an acceptor as well. In solar cells, P-doped cadmium telluride is used. However, it's difficult to give cadmium telluride a very high doping level. The structure of a typical cadmium telluride solar cell looks like this. On a glass, the transparent front contact is deposited. This can be tin oxide or cadmium stannate, which is cadmium thin oxide alloys. On top of that, the N layer is deposited, which is a cadmium sulfide layer, similar to the N buffer layer in CIGS solar cells. On top of that, a P-type cadmium telluride absorber layer is deposited with typical thicknesses of a few microns. Making a good back contact on cadmium telluride is rather challenging. The material properties of cadmium telluride do not allow a large choice of acceptable metals. Heavily doping the contact area with a semiconductor material improves the contact. However, achieving high doping levels in cadmium telluride is problematic. Copper-containing contacts have been used as back contacts. However, in long timescales they may face instability problems due to the diffusion of copper through the cadmium telluride layer up to the cadmium sulfide buffer layer. Nowadays, a stable antimony telluride layer in combination with molybdenum is used. Here we see the band diagram of a cadmium telluride solar cell. The P-type semiconductor cadmium telluride has a band gap of 1.45 electron volts, whereas the N-type cadmium sulfide has a band gap of 2.4 electron volts. Consequently, the junction is a heterojunction, similar to the CIGS PV device. The light-excited minority electrons in the P layer are separated at the heterojunction and collected at the TCO-based front contact. The holes are collected at the back contact. An important concept I did not discuss for the thin film solar cells is the two types of solar cell configurations, the superstrate and the substrate configuration. A superstrate configuration is a cell concept in which the substrate on which the solar cell is processed acts as the front window at which the light enters the solar cell. A substrate configuration is that either the substrate acts like a back contact or the back contact is deposited on the substrate. Consequently, no light will pass through the substrate. The light enters through a TCO layer deposited on top of the N-type cadmium sulfide layer. Compare this to, for instance, the thin film silicon we discussed earlier. A PIN junction is considered as a superstrate configuration, whereas an NIP junction is a substrate configuration. The cadmium sulfide, cadmium telluride layers are in general processed using the closed space sublimation method. In a closed space sublimation method, the source and the substrate are placed at a short distance from each other, like a few millimeters up to centimeters under vacuum conditions. Both the source and the substrate are heated. The source can be granulates or powders of cadmium telluride. An inert carrier gas like argon or nitrogen can be used. The source is at a higher temperature as the substrate and induces driven force on the precursors, which are deposited on the substrate. The bulk p-type cadmium telluride is formed. First Solar and Antec are companies producing the cadmium telluride solar modules using the closed space sublimation method. Among new startups moving into the cadmium telluride PV technology are Calixo, Primestar Solar from General Electric, and Abound Solar. However, First Solar is by far the largest cadmium telluride manufacturer in the world nowadays. From 2008, First Solar has an annual production rate of 500 megawatts and more, and was in 2006 and 2007 one of the biggest solar module manufacturers in the world. The record conversion efficiency of lab-scale solar cells is 18.7% as obtained by First Solar in 2013. The open circuit voltage of the record cell is 852 millivolts. The short circuit current density is 28.6 milliamps per square centimeters with a fill factor of 76.7%. General Electric achieved in the same year an efficiency of 18.3%. NREL has confirmed a new record conversion efficiency for a cadmium telluride solar module of First Solar of 16.1%. The current cost price per watt peak of the First Solar products is in the order of $68 to $70 per watt peak and is expected to drop to $40 per watt peak in the future, keeping the cost price per watt peak lower than the solar modules based on crystalline silicon wafers. An important aspect to be addressed is that the cadmium telluride solar cells contain the toxic material cadmium. However, the insoluble cadmium compounds like cadmium telluride and cadmium sulfide are much less toxic. It is important to prevent cadmium entering into the ecosystem. The question is whether the cadmium telluride modules would be a main source of cadmium pollution. A 2 gigawatt per year production capacity as installed by First Solar at the moment would take up around 2% of the total cadmium consumption by the industry and would not yet be a dominant contributor. Nevertheless, recycling schemes have been set up for installed cadmium telluride solar modules. For instance, First Solar has a recycling scheme in which a deposit of $5 per watt peak is included, which covers the cost for the recycling at the end of the module's lifetime. Maybe the biggest challenge for the cadmium telluride will be the supply of the tellurium. Here we see again the illustration that shows the abundance of the various elements in the Earth's crust. As you can see, tellurium is not a very abundant element, so tellurium supply might be the limiting step to upscale the cadmium telluride PV technology to future terawatt scales. On the other hand, tellurium as source material has only had a few users, and therefore a dedicated mining of tellurium has not been explored. In addition, new supplies of tellurium-rich ores have been found in Hsinchu in China. So at this moment it's not clear to which extent the cadmium telluride PV technology might be limited by the tellurium supply. So far we have discussed the inorganic thin film semiconductor materials like amorphous and nanocrystalline silicon, CIGS and cadmium telluride solar cells. In the next block we are going to look at organic and dye-sensitized solar cells. See you in the next block. In this block we leave solar cell technology based on inorganic semiconductor materials like amorphous and nanocrystalline silicon, cadmium telluride, CIGS and 3,5 semiconductor materials. We are going to look at organic solar cells like polymer cells or dye-sensitized solar cells. The materials used are conductive organic polymers or organic molecules. All these materials can be considered as large conjugated systems. The organic polymers and molecules consist of large compounds based on carbon. The carbon may form cyclic or acyclic, linear or mixed compound structures. Here we have some examples of organic materials used for PV applications, like P3HT, phthalocyanine, PCBM, and ruthenium di-N3. The conjugated system means that carbon atoms in the chain has an alternating single or a double bond, and every atom in the chain has a p orbital available. The classical example from chemistry classes is the benzene molecule, which is a cyclic conjugated compound. These p orbitals in the conjugated orbitals are delocalized. This means that they can form one big mixed orbital. The valence electron of the original p orbital is shared over all the orbitals. Here you see the example of the benzene ring. This molecule has 6 carbon atoms and 6 p orbitals. They mix, forming 2 circle orbitals that are occupied by, in a total, 6 electrons. These electrons do not belong to one single atom, but to a group of atoms. A methane molecule, which is tetrahedrally coordinated, has 4 equivalent sp3 hydride bonds with a bond angle of 109 degrees, as we discussed in week 2. Here we see an ethane molecule, which has 3 equivalent sp2 hybrid bonds with a bond angle of 120 degrees, plus an electron in a pz orbital. 2 neighboring pz orbitals form a so-called pi orbital. In week 2 we have discussed that 2 individual sp3 hybrid orbitals of a silicon atom can make an anti-bonding and a bonding state. The same is valid for the 2 pz orbitals, making a molecular pi orbital. They make a bond and anti-bonding pi state. Therefore, conjugated molecules can have similar properties as semiconductor materials. Most electrons are at room temperature in the bonding state, also referred to as the highest occupied molecular orbital, HOMO. The anti-bonding states can be considered as the lowest unoccupied molecular orbital, the LUMO. As the conjugated molecules are getting longer, the HOMO and LUMO will broaden and act like a kind of valence and conduction band. The energy difference between the HOMO and the LUMO can be considered as the bandgap of the polymer material. To discuss whether an organic material is p-type or n-type, we have to discuss one concept which I did not discuss so far, the vacuum level. The vacuum level refers to the energy of a free stationary electron that is outside of any material, or in other words, in a vacuum. This level is often used as the level of alignment for the energy levels of 2 different materials. The ionization energy is the energy needed to excite an electron from the valence band or HOMO to the vacuum state. The electron affinity is the energy obtained by moving an electron from the vacuum just outside the semiconductor or conjugated polymer to the bottom of the conduction band or LUMO. It means when a molecular material has a low ionization potential, it can, with a relatively ease, release an electron out of the material. It can act as an electron donor. When a molecular material has a high electron affinity, it can easily accept an additional electron in the LUMO or conduction band. Another important aspect of exciting charge carriers in organic materials is that it differs from that of inorganic semiconductor materials discussed so far. In inorganic semiconductors, we can excite an electron from the valence band and conduction band, leaving a hole in the valence band. In a semiconductor, such hole pair is weakly bound and both entities are easily separated and can diffuse away from each other. In organic materials, this is not the case. Light excitation results in so-called excitons, which are excited electron and hole pairs, which are still in bound state due to the mutual Coulombic force between the particles. the exciton can diffuse through the material. These excitons have a low lifetime in organic materials. They recombine back to the ground state within a few nanoseconds, meaning that the diffusion length of such excitons is in the order of only 10 nanometers. Let's make a solar cell out of the conjugated materials. Here we consider an organic PV device based on an electron donor type and an electron acceptor type material. Similar like for semiconductor materials, a heterojunction based on two intrinsic materials can be constructed. The junction is based on two different semiconductor materials or different conjugated compounds. Here we line up the electron donor conjugated polymer and an electron acceptor conjugated polymer. The HOMO and LUMO of both polymers can be aligned considering their energy levels with reference to the vacuum level. At the interface between both layers, we see a difference in the HOMO and LUMO levels. The difference between the HOMO and LUMO represents an electrostatic force between the two layers. The material can be chosen properly to make the difference large enough so these local electric fields are strong, which may break up the excitons. An electron is injected in the electron acceptor and a hole remains in the electron donor material. A problem of this device concept is that the diffusion length of the exciton is only 10 nanometers. It means that in this simple configuration the thickness of the solar cell is limited by the diffusion length, while the thickness has to be at least 100 nanometers to absorb enough light. Therefore, the organic solar cells are based on bulk heterojunction photovoltaic devices. In such a device, the electron donor and the electron acceptor materials are mixed together. Typical length scales of the mixture of the blend equal to the exciton diffusion lengths can be achieved. As a result, a large fraction of the excitons excited in the material due to light absorption can reach an interface where they are separated into an electron and a hole. The electrons move through the acceptor material to the electrode. The holes move to the donor material to be collected at the other electrode. The holes are usually collected at a TCO electrode like ITO. The electrons are collected at a metal back electrode. The record organic solar cells are based on double junctions nowadays. Heliatech achieved a 12.0% solar cell efficiency on lab scale. The stability of these cells is unknown. An advantage of organic solar cells is that they have a low production cost. Chemical engineering allows a large flexibility in bandgap engineering. The organic solar cells can be integrated into flexible substrates. Important disadvantages are a low efficiency, a low stability and a low strength compared to inorganic PV cells. Although organic solar cells can be cheaply, the need of highly expensive encapsulation materials to stabilize the organic PV products limits the industrial application. To my knowledge, no company is producing organic solar cells at the moment. Konarka Technologies has been active in the past. The small modules had efficiencies in the range of 3 up to 5% and lasted only a couple of years. An alternative solar cell concept based on organic materials is the so-called dye-sensitized solar cell. It's a photoelectrochemical system. It contains titanium oxide nanoparticles, dye particles, an electrolyte, and a platinum contact. In this illustration, the dye-sensitized solar cell is schematically shown. Let's consider first the photoactive parts of the solar cell, which consist of the photoactive dye sensitizer, which acts like an electron donor. The second material is a titanium oxide nanoparticles, which acts like the electron acceptor. The dye material is mixed with titanium oxide material like organic bulk heterojunction solar cells. The photoactive material is the so-called dye photosensitizer, ruthenium polypyridine. If a photon is absorbed by the ruthenium polypyridine, it can excite an electron from its ground state referred to as S to an excited state referred to as star. In this case, the S can be considered as the HOMO and the S star state can be considered as the LUMO. The S star state lies higher in an energy than the energy level of the conduction band of the titanium oxide. As a result, the light-excited electrons are injected into the titanium oxide nanoparticles. The photosensitizer molecule remains like a positively charged entity. The electrons in the titanium oxide move to the TCO-based back contact. The transport mechanism is diffusion-based. The electrons diffuses between the various titanium oxide nanoparticles until they arrive at the TCO contact. Through the electric circuit, the electrons move to the counter electrode, in other words, the other contact. Between the counter electrode and the die, a so-called electrolyte is placed. Electrolytes are solutions or compounds that contain ionized entities that can conduct electricity. Typical electrolyte contains iodine. The positively charged oxidized dye molecule is neutralized by negatively charged iodide. 3 negatively charged iodides neutralize 2 dye molecules and create 1 negatively charged triiodide. This negatively charged triiodide moves to the counterelectrode where it is reduced using 2 electrons into 3 negatively charged iodines. These photoelectrochemical cells require a platinum back contact to facilitate the reactions. As a result, the performance of a dye-sensitized solar cell depends on the HOMO-LUMO level of the dye material, the Fermi level of the titanium oxide nanoparticles, and the so-called redox potential of the iodide and triiodide reactions. The record efficiency of dye-sensitized PV device on lab scale is currently a 14.1% as achieved by EPFL in Switzerland. The advantage of dye-sensitized PV devices are the low cost price of producing the device. A disadvantage is the stability of the electrolyte under various weather conditions. At lower temperature, the electrolyte can freeze. This stops the power production and it might result in physical damage. Higher temperatures result in significant expansion of the electrolyte, which make encapsulation of modules more complicated. The dye-sensitized PV technology is facing some more challenges. One is replacing the expensive platinum electrode material with other cheaper materials. The second one is the development of more stable and resistive electrolyte materials. The third one is the development of improved dyes, improving the spectral and band gap utilization of the solar cells. A dye-sensitized PV product is not yet available on the commercial market. In this week, I have introduced you to various PV technologies. Next week, we will shortly discuss the so-called third generation PV concept. In addition, we will look at alternative solar technologies which not only produce electricity, but heat or solar fuels as well. See you next week.